before continuing on the presentation, oh, I'll just switch off my video just to make sure I don't have any network issues. And during the question answer session, we will put it back on. So I hope you all can see my screen. So this is from one of our recent studies that we from a paper that was at HFTC 2025, and it's from a consortium with a lot of different companies. So a lot of different colleagues have had contributions into this study, and I'm kind of integrating everything and just compiling the results. So we're going to talk about how long does a hydraulic fracture drain. So whether do we drain from really close, do we go till the tips, kind of how far does the proppant go, and it's mostly insights from some modeling studies, but backed by data which have which has been collected in recent projects. Uh, oh. So yeah, this is the paper I was talking about, and as you can see, we have a consortium with a lot of different companies, and I'd like to acknowledge all of the colleagues from these companies and for their contributions, especially in kind of allowing us to use the data and kind of present. And we've also, in this study, we have made public some of the numbers related to what's the fracture conductivity like, for example, fracture dimensions. So that's kind of really useful to put into context and kind of gives us some idea about what we are talking about. So yeah, just that's the reference for all of you. So what was the motivation behind the study? So we've had a lot of projects where we've had diagnostics from fiber, microseismic, and kind of the core through studies in HFTC, which have given us great insights into what's happening in the subsurface during hydraulic fracturing and subsequent production. I think a lot of the pioneering work has come from HFTS1, HFTS2, and also from the Retterman et al. Paper series from ConocoPhillips with kind of these code through which gave us insights on how hydraulic fractures are propagating. An example of a fiber study from Ugueto et al. Where they kind of showed that most of the fractures were along SH max, and that's what we got from the Ratterman et al. Study as well. This is from the HFTS2, where the fiber data showed kind of how we can constrain the height growth. So again, a lot of new insights about hydraulic fracturing over the past few years. So we kind of know which directions fractures go, how large fractures are from fiber data, from seal wellbore pressure monitoring, etc. The one gap is kind of the propped part, or what part of the fracture is the producing fracture. Is it the And that's, as we know from experience, it's substantially shorter than the full fracture length. So what's the propped length? Is the pressure uniform across the fracture? Are we talking about a constant conductivity within the propped length, and how does that change over time? Are some of the questions that have been challenging to answer in the models, and have been difficult to constrain, primarily because of lack of suitable data. So that was kind of the motivation behind this study. Um, and it's kind of, when we talk about what's happened in the far field, if we know that, that removes the non-uniqueness from the model. So I have an example over here. This is from Garrett Fowler's and others' paper in 2019 from the Utica, where they did a production history match of in a particular field in the Utica with a low permeability realization and a high permeability realization. And you can see the production history match looks pretty good with both cases, but the fracture dimensions that you get and kind of the insights that you get from both the models will be drastically different, because you're assuming kind of a magnitude of order different permeability in this case. And for instance, when we make a decision like well spacing, you will come up with completely different conclusions depending on which realization you think is the correct one. An example over here of, if you do a curve of NPV versus well spacing, you will be at a drastically different points in time where you will have your optimum well spacing, depending on whether you think that the permeability is 25 nanodarcy or 850 nanodarcy. And that's because we have this non-uniqueness, because the production depends on the a square root of k and how it changes with time. And we are often not able to kind of differentiate how big the propped area is, or what's the permeability from two different independent sources. So we often have this non-uniqueness. So what's the best way to break the non-uniqueness is to map the far field pressure distribution. So for example, if we knew that at this distance we have significant depletion, we would be able to rule out this the high permeability realization, because kind of we'll be able to constrain our propped lengths better. So again, it's very important to remove non-uniqueness from the models, and the best way is to get some idea of the far field drainage along the fractures. Uh, how do we know the far field drainage along the fractures? So a few different methods. Something that's becoming more common, fortunately, these days is interference testing. If we have two wells and both are hydraulically fractured, and both are shut in, and we start producing one and we observe the pressure on the other, then we get an idea of what the interference is like between those two wells. And if, for example, we have studies from recent years where the interference tests have been repeated at different points in time, it gives us an idea of the connectivity between two different wells at a given distance after, let's say, immediately after the stimulation or after 1 year or 2 years or so on. This is a paper, Al-Masudi et al., which we've worked along with Devon, and we came up with the DQI method, which kind of is a new method to interpret these interference tests and get a good idea of what's the degree of production interference. So I think interference tests are a good, relatively inexpensive way to get a good idea of how the far field depletion is going. Uh, and again, on the right, we have these two examples from recent projects. This is from a pretty well-known Exxon paper where we have a producer well, and then we had two monitoring wells which are drilled at different angles with a vertical offset and horizontal offset. And we have far field pressure gauges along this lateral. And what we know from this project is, so for instance, along the toe, we can see the far field pressure drainage at a shorter distance, and towards the heel, we can see the far field drainage at a larger distance. So this gives us a pretty good idea of how the far field depletion changes with distance from the production well, both in a horizontal plane and in a vertical plane. So again, pretty amazing data. And I'll show you our history matching for this and what insights we got from that. But yeah, it kind of gives us pretty good insights of how far field depletion looks like. A pretty similar, again, a well-known paper from Craig Cipolla and Hess, where they have an observation lateral over here in the Three Forks, and we have producing wells from the Middle Bakken, and we have both fiber and pressure gauges in this well, and then we can see how the pressure decreases through time in the monitoring well when we are draining and producing from the offset production well. So again, we have an idea of how steep or how gentle the depletion is at the far field and how it's changing with time. So again, with the influx of these new data sets, and when we combine them with fiber and everything else, we start to get a good picture of how the hydraulic fracture is draining, especially when we go away from the production wells. Um, it's a bit of a wordy slide, but kind of there's lots of things to unpack because we used a number of these data sets. Uh, so essentially, the crux of the project is that we used four shale data sets, two in the Bakken, one in the Delaware, one in the Midland. So we have some diversity in terms of basins as well. And we integrated high fidelity measurements, including two pressure monitoring laterals from those two projects that we showed you, and two other projects from where we had interference testing data in addition to other data as well. And we are able to build a pretty clear picture of fracture propagation, proppant placement, and depletion, and try to kind of integrate all those three aspects together. Um, I'll kind of go through the key takeaways pretty quickly now, and then once we see some examples, maybe we'll revisit this at the end, and then maybe we'll discuss this during the question answer session as well. Uh, so we see that the proppant placement in shale is sparse, so very low kind of concentration values, 0.07 to 0.25, uh, and yeah, depending on proppant trapping, and we'll talk a lot more about proppant trapping as we go along. Uh, so propped fractures are finite conductivity, as we realized from matching these diagnostics. And we have thousands of psi's of pressure drop across the productive length. And the conductivity of the fracture decreases as we go away from the well. It's not a constant conductivity fracture till the end of the proppant, but there's a gradual decrease in conductivity as we increase the distance from the well. Um, and there's a significant time component as well. So the fracture conductivity appears to decrease both as a function of drawdown, which is because we increase the effective normal stress on those fractures, so the fracture conductivity declines, but also there's a time component to it that even if we have the same drawdown, the fracture conductivity still declines with time. And that's pretty clear when we look at those diagnostics. In this paper, we have given our calibrated values of the fracture conductivity and some of these model inputs that we hope can be kind of a start of a discussion, and then we can compare on the different values that we need to use across different geological settings. Uh, Now, a pretty key point of the whole study is that the proppant holdup against asperities appear to be a key factor in preventing proppant settling. So as we know, the fractures are not plain uniform surfaces, but have a roughness. There's also undulations caused by maybe natural fractures or some localized changes in stress. Uh, so we have the proppant doesn't necessarily kind of fully settle down or go as far as we think it would, but there is some degree of proppant trapping that occurs due to kind of that unevenness in the fracture. This reduces prop length, uh, and we'll talk more about that. And we found in this study that it's affected by the proppant size. So for example, a smaller proppant can go farther. Geological setting, different basins have different typical proppant trappings, and potentially flow rate, so higher flow rate can make the proppant go farther. And that's something that we are still investigating. Another key point, since this being ARMA and kind of that was my PhD topic, is that uncertainty in the stress or pore pressure profile above and below the pay zone creates a significant non-uniqueness and uncertainty. Even so, for example, even when we know the height of the fractures from the diagnostics, but we don't know the stress profile, that creates a non-uniqueness in the model. And as always, it's best to take more stress measurements above and below. I know it costs money, but yeah, it there's no harm in asking. So yeah, that's kind of the overall takeaways from the project. I kind of wanted to give them before I go into the details, so you kind of have it in the back of your mind and are able to kind of relate the different examples to what I'm talking about. Um, yeah, simulation approach. A lot of you might know about ResFrac. It's a fully coupled and integrated hydraulic fracturing software code, fully 3D, and we're also accounting for poromechanical stress changes induced by depletion. So yeah, kind of to clarify that. Uh, Model calibration process, kind of how we go about it is we set up the initial model with the static model, the geological model, well geometry, frac schedule, etc. And then we build a list of key observations, and I'll give an example from some of the data sets of the key observations. And the idea is to get a list that summarizes the main results from the diagnostics, the frac data, the production data in each data set. And then we have certain key model parameters on the field scale, and some of these cannot be measured in the lab because they are very scale dependent. And then we vary these parameters and try to see kind of what values make sense physically in terms of the physical constraints, but also are able to calibrate the data pretty closely. And kind of the final step is once we have a calibrated model, then we do sensitivity analysis and or optimization to answer specific questions about the hydraulic fracturing design. So that's kind of an idea about the model calibration process, of which we'll see a few examples as we go on. Um, I probably kind of won't go through this in details, but some of the typical parameters that we're talking about uh, where that will vary is the fracture toughness and the fracture conductivity during propagation. These would control the fracture length. We'll have the stress profile and toughness anisotropy. So stress profiles is mostly what we have computed. Toughness on a field scale is more uncertain, and that's a calibration parameter. Then proppant immobilization or proppant trapping, which controls how much of proppant is trapped in the asperities and how much of proppant is allowed to go farther in the fracture. That's also a key calibration parameter. Then we have permeability, how it changes with time, and also the proppant conductivity. and how the proppant conductivity changes with drawdown and time. Of course, the usual parameters for the production part, relative permeability curves, time-dependent conductivity loss, which we'll mention, and the fractal dimension, which I'm not going to talk about too much today. But yeah, that's probably, I think there have been a couple of other talks kind of talking about the fractal dimension. Um, I, I'll give you one example of how one of these parameters. So if I go back over here, so we're talking about the fracture conductivity during propagation. The way we control that is by using this effective fracture aperture conductivity factor. So when we have a lower factor, it decreases the fracture conductivity during propagation. So it induces a more viscous pressure drop along the fracture surface between the well and the fracture tip. When we have it closer to 1, then the fracture conductivity is just as computed by the cubic law. So when we have, for example, uh, effective fracture aperture conductivity factor of 1, uh, the fracture propagation is entirely or primarily controlled by the stress shadow. So that's why you will see a significant asymmetry. In this case, there's an angle between the SH max and the well, so that which leads to an increased asymmetry. Now, as we decrease this, so for example, we go from 1 to 0.4 to 0.2 to 0.1, it decreases the fracture conductivity during propagation, which results in a significant pressure drop in the fracture. So, uh, kind of trying to mimic the viscous pressure drop along the fracture surface, and that results in more symmetric fracture. So, depending on what we have in terms of the fiber observation, for example, in terms of fracture geometry, the fracture geometry in the model would be a function of the fracture conductivity during propagation, toughness, and leak off. So those would be the primary parameters to give you an idea of what we are talking about. Um, Another kind of when we talk about proppant trapping, so let's say if we don't have any proppant trapping in the models, what usually happens is if we, with the physics of the proppant transport, if we have something like a proppant distribution as shut in that looks like the figure on the left, eventually, uh, once the fracture starts closing down, the proppant settles pretty quickly at the bottom, and then we used to see a lot of these models where there's like disconnected amount of high proppant concentration at the bottom and not that much of proppant close to the well. So to kind of solve this theoretical problem in proppant transport models, um, and from production data and from kind of we also have evidence now from vertically offset observation wells with pressure gauges. So we know that that's probably not true, and the proppant's pretty well connected to the well bore. So that's where we have this proppant trapping. Uh, so with trapping, our propped length becomes less since we are trapping the proppant at each element of the fracture, and we specify kind of a proppant trapping concentration. And this is the at the end of the injection, the proppant concentration map uh, with proppant trapping included in the model. And we still have settling, and you can see kind of there is still a high concentration of proppant at the bottom, decreasing concentration kind of as we go up due to settling. But we still have a significant amount of good vertical proppant placement, which is more consistent with what we see from field data. So kind of this suggests that we have both proppant trapping and settling occurring, but then proppant trapping is a significant constraint on the propped length. Uh, so yeah, that's kind of the idea behind proppant trapping. Yeah, so another kind of thing to keep in mind is as we have less trapping, the proppant travels farther along the fracture. So for example, figure on the left, we have a maximum immobilized proppant, the parameter which controls the proppant trapping of 0 0.6 pounds per foot squared, and on the right is 0.1 pounds per foot squared. So you can see the fractures going out farther compared to the figure on the left. So figure on the left will have a higher conductivity of proppant since the concentration is higher. Figure on the right will have a higher a square root of k, and kind of both are important for production because production's dependent on a square root of k, but if the conductivity decreases too low, depending on the drawdown or conductivity loss with time, we also have a degradation of production. So that's where kind of getting the proppant out further, but yet maintaining a good proppant concentration close to the wellbore is the Goldilocks zone for production, as we've seen in most of our models. Now let's talk a bit about the data sets and what we learned from them. The first data set that I'll talk about is the Midland Basin data set where the target was Wolfcam B. In this data set, we had in-well fiber, cross-well fiber, interference testing, and production. So we get a good idea of the uniformity and of the fracture distribution. So for example, what's the cluster efficiency? Are all the fractures symmetrical, or is there kind of significant non-uniformity between the different clusters? Crosswell fiber gives us a volume to first response and tells us how far the fractures have gone and what's the rate of fracture growth. Interference testing tells us how the fractures are conducted, are connected hydraulically. So for example, sometimes we notice that we say there are a significant number of frac hits on the fiber, but the interference testing shows there is no interference. Probably the explanation could be that the proppant hasn't reached. It's just the hydraulic connection that is seen on the fiber, but the interference testing gives you a very good idea of a propped and productive connection between the two fibers. And of course, we have to kind of calibrate everything to the production data, which is the ground truth. Some examples over here. So this is a cumulative production oil history match. We have RTA plots. So we try to kind of match these bend in the RTA curves. So for those of you who may be familiar, the slope of the RTA curves kind of tells us on how productive a well is. And when the slope changes with time, it tells us that either we are losing permeability or productive area with time. This is a example of a GOR and a water cut calibration. And this is kind of what the fracture geometry looks like for this data set. And yeah, this had a very extensive monitor of fiber observations, and we had observations both in the same zone in the Wolfcam B1 and Wolfcam B3, and across zones with, for example, a stimulation well in the Wolfcam B1 and a monitoring well in the Wolfcam B3. So kind of pretty extensive fiber geometry that we got both in the same zone and out of zone as well. An example of the key observation table that I was talking about. So, and I've already mentioned a lot of these is the fracture hit timings from the fiber that gives you an idea of how fast the fracture is growing, wetted fracture lengths, which is from the frac hits in the fiber data, cluster efficiency, which is from the in-well fiber data when we look at kind of how the fluid is distributed across the different clusters. And then this interference test between the wells, this gives us a good idea of how the proppant is connected. And in this case, in this data set, we were very fortunate that the interference test was not at the beginning of production, but at 16 months after the start of production. So this is a pretty good calibration of how the long-term far field drainage looks like. So after 16 months, when we've already had some drawdown, effective normal stress on the fracture is high, how connected are the wells in terms of the conductivity of the connection between the two wells? And I've also listed, for example, what model properties are we changing to calibrate? So for example, for interference testing, we would need to calibrate a proppant conductivity, how the proppant gamma, which is how the proppant conductivity changes with effective normal stress, proppant conductivity loss function with time, and proppant trapping, which is how far the proppant is gone. So kind of pretty extensive data sets, which reduces the non-uniqueness to a large degree. Of course, in this data set, we also had early time interference testing. So again, if we connect the early time interference test and the late time interference test, we have an idea of how the productivity of the propped part of the fracture has changed with time. I have some examples over here of the frac hits that we were talking about. So we had an idea of what's the largest distance at which we have seen frac hits across zones or in the same zone, and what's the smallest distance where we see no frac hits. So again, a pretty good constraint on the maximum and minimum fracture lengths that we were able to get from the fiber. Again, this observation table is to give you a flavor of how the calibration process was done and how kind of we end up matching uh, uh, um, matching all the data that we have. Yeah, this is the second Bakken. This is the Bakken data set. This is an observation lateral, and it's summarized by Cipolla et al. 2022. We have cross-well fiber, cluster efficiency, and far field depletion measurements. So this is an example of that I mentioned before, where we have this well where we are observing the pressure changes as we are producing from the other wells. And we also had a measurement of the production and interference testing. So pretty extensive kind of data set over here. Uh, the second Bakken data set, and kind of now I'll show some insights from the two Bakken data sets, which is interesting because we have two data sets in the same basin. So in this data set, as I mentioned before, we have this offset well pressure gauges at different distances. And kind of the most interesting part is we see that those gauges deplete till different extents. So for example, gauge 1 is the closest gauge which depletes the most. Gauge 4 is the farthest gauge which depletes the least. So over here we have time, y-axis is pressure at these different distances from the production well. And similarly, with this vertical offset well, we have a similar idea of with increasing distance, you see lesser depletion and higher pressures. As we come closer to our production well, we see more depletion and lower pressures. We also had fiber where we could calibrate on, for example, at this distance, we had 100% frac hit efficiency from the production, from the well that was stimulated. At this farther distance, we only have about 30% frac hit efficiency. So only about one third of the fractures were going this far, but 100% of the fractures were going till about this distance. Similarly, with the vertical offset well, we could see that for the given distance, all of the fractures, so we had 100% efficiency till the farthest gauges. So we have a pretty good handle on how the fracture lengths are distributed and how the proppant is distributed and how conductive is the proppant when we combine all these observations. Here's an example of the calibration. The stars are the kind of frac hit efficiency at the different distances in the model. So you could see we match these pretty closely. This is the production match, and this is how the fracture conductivity looks like. So you can look at our scale over here. You can see at some distances, the fracture conductivity changes from the red to kind of 1 million RC feet and below when we start looking at different observation distances. And oh, okay. Well, now I'll maybe take some time for to explain this slide. So what we have on the figure on the bottom right is the pressure at a given time. So for example, if we look at this plot and then we take snapshots at different points in time, and we plot on the x-axis the distance, on the y-axis the pressure, then what we are going to have is this curve where the pressure is changing with distance. So for the gauges that are closest to the producing well, we have the highest amount of depletion, so lowest pressure. The gauges that are farthest have kind of the lowest amount of depletion, and we have snapshots in 6 months, 1 year, 18 months, and 2 years. And the dots are the equivalent from the model. So just kind of showing the calibration that we did at different points in time. Now, one interesting thing is that the pressure gauges, these appear to show the pressure in the fracture and not the matrix. How do we know that? It's so monotonic. There is kind of less random variability. So it appears as if all the pressures are connected across and related to the distance along the fracture from the well and not related to where they are positioned in between the fractures. So that seems to be pretty clear, unlike maybe in some other data sets where that may not be the case. And fracture conductivity appears to decrease with distance from the well, as you can see kind of with the decrease in depletion. And if we compare the lengths till which we have significant depletion, so for example, over here, which is significantly less to the length till at which we have the frac hits from the fiber, which is maybe over here. And then we can kind of see that appearing to be true at all points in time. We have this high depletion zone, a medium depletion zone, and a low depletion zone. So showing that the fracture conductivity appears to decrease with distance away from the actual production well. Uh, Now, this is kind of one of the major insights that we have from the paper. Um, so on how the fracture conductivity changes with drawdown and time. Now, the Bakken 1 dataset, which we calibrated some years ago, uh, so to match kind of the production or the drawdown at a given distance from the pressure gauges with time, we had to use very steep profiles of fracture conductivity with effective normal stress. So you can see kind of we start out with a high conductivity, and then we have to make it steep with effective normal stress, and that's to match kind of the early observations in the pressure gauges and the interference testing. So if we combine all the data, we have to use these steep conductivity curves. Whereas for the newer data set BK2, we used kind of much more what we call regular or non-customized fracture conductivity curves with effective normal stress. So, however, to match the Bakken 2 dataset, we had to use a proppant. There's a conductivity loss with time. So we used these functions. So these are the functions that we used for the different datasets where x-axis is the time, y-axis is the damage multiplier. And for different datasets, we have to use a different extent of these conductivity loss with time. Now, the physical mechanism may be some sort of a plastic deformation of the proppant, fines migration, maybe some chemical damage because of hydrocarbons or some kind of a hydrocarbon residue. We're not sure, so it might be a combination of those mechanisms. But it does seem for pretty certainly that the proppant conductivity is changing with time, and and that the conductivity even when we have a constant drawdown. So for example, when we are producing at constant bottom hole pressure, the proppant conductivity goes down with time. And kind of this data set where we take snapshots after 6 months, 1 year, 18 months, and 2 years, we get this fact that the pressure distribution stabilizes over time in the far field gauges, even though we are producing, which means that the reservoir itself continues to deplete. So you can see kind of if you look at these intermediate distances, the pressures do not change that significantly, which means that for this to be true, the proppant conductivity is going down with time. Otherwise, we will have continuous depletion at these distances with the given production. So that kind of gives you a pretty good idea that in addition to effective normal stress, there's a significant time dependent component to the fracture conductivity. And that's kind of an important insight that we've got from integrating all these data sets. Um, so another thing is to do a lot of these history matches, we had to have the proppant trapping as a function of the proppant size. So the maximum immobilization that I was talking about. So some proppants, it seems, get trapped closer to the wellbore, whereas some proppant go far from the wellbore. I have an example of a function that we needed to use as a function of mesh size. So this is a proppant immobilization multiplier. So for example, I'll just kind of use random numbers. For example, if we have a 40 mesh proppant over here, then we have a higher proppant conductivity, proppant trapping multiplier for it, and we have, let's say, a 200 mesh proppant over here. It has a really low proppant trapping multiplier. So in essence, the 200 or the finer proppant will go farther, and the coarser proppant will get trapped closer to the fracture. And it seems pretty intuitive that given the asperities in the fracture, we will have the larger particles get trapped a bit closer. And from the optimization simulations that we did from the sensitivity analysis, it's beneficial to have both because the larger proppant gives you the conductivity closer to the wellbore, whereas the farther kind of increase in the a square root of k is given by the finer proppant. So again, in terms of, it seems as if both a distribution of proppant sizes seems to be beneficial. But of course, it will depend on the individual case. Uh, here's an illustration of how the proppant conductivity is changing with time. So on the top, we have the BK1 dataset where we had the proppant conductivity as a strong function of effective normal stress, but not as a strong function of time. So you can see kind of from 6 months to 2 years, we have a significant decrease in proppant conductivity. So this is on a log scale. So you can see overall the proppant conductivities are kind of less than 10 millidarcy feet for most of the propped area. After 2 years, we have a significant decrease in proppant conductivity because of drawdown. You can see the colors changing from this yellowish color to more of the greenish color. And our effective production area or the effective productive area has decreased quite significantly. But now our kind of we reach a constant bottom hole pressure condition. Our drawdown is not changing that much. So the proppant conductivity stabilizes with time. Whereas for the Bakken 2 data set, where we had the far field pressure gauges at different distances, we needed to use a very strong time function. So we had this a slightly higher conductivity early on, still kind of proppant conductivity less than 10 millidarcy feet overall. After 2 years, kind of we are sub 1 millidarcy feet, and after 5 years, everything is less than about 0.25 millidarcy feet. So again, fractures are finite conductivity. Fracture conductivity changes with distance from the fractures, from the wellbore, and fracture conductivity decreases as a function of drawdown and effective normal stress. We've kind of in the paper we have tabulated these values, so when you do your own models we can have a good comparison and see kind of if there are different values in different basins. From this study, at least it looks like in the Midland Basin we have slightly higher conductivities, and the Delaware Basin as well, and maybe in the Bakken we have slightly lower conductivities, although there's significant difference between the two Bakken datasets. Uh, so now coming to another learning when we did the calibration for all of these data sets is the importance of stress profile. Uh, so again, we often have a lot of uncertainty in the stress profile, and that's primarily because the stress measurements that we get are restricted to just the landing zone. Now, in this case, I have the stress profile that we got from the operators for the Bakken 2 dataset on the left and the Bakken 1 dataset on the right. So you can see it's pretty much a different approach of using kind of a more extensive stress profile or a more simple approach. Again, both have their pros and cons because there's a significant uncertainty in the lodgepole because of a lack of measurements. Uh, but the issue is that from the fiber data, we had a similar kind of idea of height growth in both of the projects. So when we look at the fiber, the distance at which the fractures have grown into the lodgepole seems to be pretty similar. Uh, in the BK2 dataset, the operator believes that there is significantly lower pore pressure in the lodgepole, so which leads to this lower stress value. And in BK1, kind of the operator used a pretty simple approach and used a pretty consistent stress in the lodgepole. So this, because the stress was pretty straightforward, was very easy to match. In this case, we had to do some analysis and an automated history matching analysis, and we came up with this stress barrier, which is conceptually kind of in agreement with what the geoscience team of the operator felt as well, that there is some kind of a stress barrier at the top of the Bakken and the lodgepole. And after the stress barrier, there's a ramp which leads to decrease in stress in kind of when we go further up in the lodgepole. So we had to introduce and make this stress barrier a bit stronger to match the height growth that we observe from the fiber data. Um, so again, in both cases, the height growth is calibrated to what we see from the fiber measurements. So those are accurate, but we had to use different parameters in terms of the fracture toughness, for example, toughness anisotropy, because of the different stress profiles. While height measurements are useful, along with the height measurement, we definitely need kind of more stress measurements in the overburden and also the underburden in a lot of different cases, or those would be very helpful. And again, we've all worked on different methods to calculate stress from log data, but kind of the reality is uh, without accurate stress measurements, all of the methods are kind of pretty uncertain when we don't have enough measurements to calibrate by. So calibration is the key for stress profiles. And yeah, kind of one of the key messages is it would be very helpful if we have a series of mini frac tests along a vertical pilot hole. Whenever we have had a data set like this, it reduces kind of the non-uniqueness on the fracture height growth parameters like toughness, anisotropy, etc. So again, very useful to have and reduces the uncertainty quite significantly. Uh, and again, depending on the stress profile, the fracture geometry looks very different. And similarly, the far field depletion looks very different. So for example, if we contrast the Midland Basin dataset on the top and the Delaware Basin dataset on the bottom, because of the stress profile, so you can kind of see this stress profile, there's lots of stress barriers. We get these longer, thin fractures, uh, which kind of agrees with what we see from the interference testing, that we see a significant interference at larger distances. Whereas if we look at the stress profile in the Delaware Basin, we have stress significantly decreasing as we go up in the bone springs, and we get a significant amount of height growth. For those of you who might be familiar with the HFTS2 dataset, also in the Delaware Basin, where they had a fiber data and were able to see, uh, I may be wrong about the exact number, but I believe it's in the order of 1,000 to 1,500 feet of height growth along the fiber, which of course we would have never believed if we did not have fiber. But then when we look at kind of some stress profiles and then we model that, seems to be pretty easy to match uh, given a kind of a reasonable stress profile in the area. So again, when we have less height growth, potentially we have longer productive distances. When we have higher height growth, the far field depletion distances are smaller because more of the fracture energy is spent in the fracture going up or down. So it's pretty important to constrain the stress profile to know how far the wells are depleting. And again, so stress profile is an important contributor to the decision of how far the well spacing should be. So finally, I have some learnings from the Delaware Basin dataset. Kind of, it has a different flavor to some of the datasets that we have talked about before. So in this case, we had in-well fiber data and perforation imaging. So a pretty good idea of how the proppant is distributed or the erosion is distributed across the different clusters. We have kind of there's a separate paper by Yegor kind of focusing on the physics of the proppant transport. We also have crosswell fiber in this case, but kind of the unique thing was that we had production logging by stage, and the stages have different stage lengths, which I'll kind of show a bit more detail on the next slide, excuse me. And we also had the interference testing. So I show a calibration of the production over here. Dashed line is the actual data. Solid line is what we got on the model. So a pretty good production history match over here. We have pretty good agreement with the fracture height growth from an analog fields in the Delaware Basin. And yeah, we have this configuration where we have the wells landed, 3 wells landed in Wolf Camp A and 3 wells landed in the third Bone Springs. The Dulhoya et al. 2022 paper has a lot more details about the setup and kind of the design of the experiment. So what do we have in this case? A pretty unique experiment where across the lateral, we have 4 different designs. Uh, in the first case, we have in all the cases, we have a cluster spacing of 25 feet. In the first design, we have 4 clusters. So this is a 100 feet cluster, 100 feet stage with 4 clusters, 200 feet stage with 8 clusters, 250 feet stage with 10 clusters, and 350 feet stage with 14 clusters. So we have a pretty good data set of how the well is behaving with changes in design of the stage. And what they found in the actual data is that from the production logging is that the shorter stage lengths did significantly better in terms of the production compared to the longer stage lengths. And also when we look at the perforation imaging or the fiber, on this plot, we have uniformity index on the y-axis and different designs on the x-axis. The shorter stage length, that's 100 feet, has a significantly higher uniformity compared to, let's say, the 300 feet or the 200 feet. So longer stage lengths leading to shorter uniformity. The red rectangles are the calibrations from the model. So we were able to reasonably replicate the changes in uniformity with changes in stage length. However, the model, as we're using our regular default parameters, we were unable to explain the differences in production with stage length because we had the changes in uniformity, which makes the shorter stage lengths more productive. But the amount of production difference that we observe was significantly higher than what the model could explain. The Duldoya et al. Paper has some numbers on kind of what magnitude of production difference we're talking about. So if we look at production per feet of lateral length, we're talking about a 50% difference in production per feet, depending on stage length, in terms of to give you an idea about the magnitude that we're talking about. So then we thought what hypothesis we could use to explain the fact that these higher production rates are associated with the shorter stages and with lesser clusters, whereas the longer stages with more clusters have a lower production rate. And one of the ideas was since we have a similar pumping rate for all of these stage designs, what's different is the pumping rate or the injection rate per cluster. So injection rate per cluster is significantly higher for the 100 feet compared to the 350 feet because the same rate is getting divided for the 14 clusters. So kind of our idea was, if we think in terms of the physics, when we have a higher flow rate per cluster, it potentially is pushing the proppant out further. So we have a higher propped area and a higher a square root of k. Similarly, when we have a lower uh, a pumping rate per cluster, we are unable to push the proppant out farther from the fracture. So we have a lower a square root of k. And so, for example, if we plot the average velocities, in these two cases, in the bottom, I show some fracture results from the 100 feet model with 4 clusters. This is a 200 feet model with 8 clusters. So if we look at the average velocities, or if we look at the flow rate per length, they are significantly higher because the flow rate per cluster is higher when we look at the shorter stage length with lesser clusters. So we thought if we make the proppant trapping dependent on this, then maybe we can get a good match. And yes, when we did that, that was the only way in this model to explain the differences in production, or to explain the fact that the shorter stage lengths had a larger propped area and hence larger production, whereas the longer stages with more clusters have the shorter propped area and hence lower production. So again, that was the only way. The other differences between the stage lengths, such as differences in uniformity, differences in how the proppant or the fluid is distributed across fractures, was unable to explain the differences in production. So again, maybe a pretty good insight about the fact that the stage design that we do, or how much flow rate or proppant concentration we have, might be a factor in how far the proppant is going along the fracture and how long our a square root of k is. Of course, this is just one data set, and kind of we are trying to look at a lot more data sets that we analyze to see if we see a consistent trend like this across different data sets. Um, so again, in terms of, I know I've kind of gone through a lot of different aspects of these data sets, but we were trying to integrate a lot of different diagnostics across the fiber with fracture lengths, fracture geometries, fracture heights, production, far field drainage, and interference testing. Uh, so what we realize is, with a combination of in-well fiber, far-field fiber, seal well bore pressure monitoring, perforation imaging, and far-field pressure monitoring, we can have a pretty clear picture of not only where the fractures are propagating and where the proppant is placed, but where the production's happening. And that's the kind of the key aspect that we've studied over here. So again, pretty remarkable on how the diagnostics have come along in the last few years. Uh, when we look at the far field drainage at different distances, and we look at kind of look at those plots of how the depletion is changing with distance, we know for sure that the depletion is not infinite conductivity, but there's likely a very large pressure gradient across the proppant pack. And again, because we had along at different distances, we had a pretty clear relationship of distance with depletion. And we know the conductivity of the proppant decreases with drawdown, and also very likely decreases as a function of time. Was pretty evident from the data. If we look at the far field depletion data sets and the fiber, pretty clear that the proppant does not reach the fracture tip. So our effective productive propped area is significantly lower than the fracture area. So proppant trapping plays a key role in that. So a lot of the proppant gets trapped and does not kind of travel along the fluid till the tip of the fracture. And also proppant trapping, as we see in the model, improves vertical placement, which is also what we observe in a lot of these diagnostic data sets. But greater trapping also decreases the propped area. And again, that was what we saw with the different stage lengths in the Delaware Basin dataset. So these processes of proppant trapping, for example, in a physical sense, it might be fracture roughness or some other aspects of the fracture. And whatever controls the proppant trapping and proppant pack conductivity will have a major role in determining production. When we look at more basins, we will get a better idea of how the variation, if it's consistent across different geologies, or how much dependence on the rock type is there for these kind of features. We rarely have measurements of stress above and below the target zones, and this creates an uncertainty. And I think, as we always say, more stress measurements are always good, more the merrier. But more importantly, we need kind of a distribution of stress measurements both above and below the pay zones, as that will make the picture clear of where the fracture is going. So yeah, that was what I had to present. And yeah, I leave some time for questions.
And thank you, Ankush. Really a lot of great information there. That was a fantastic presentation.
Thank you, Sean.
And you do have a couple of questions.
Yeah,
Some of them are clarification questions.
yeah.
So the first question is, there may not be a generic, there may only be a generic answer to this. What size and type of proppant are you considering for the conductivity calculations?
Yeah, so because these are operator data sets, I cannot say the exact size, but these are like the proppants that we use. So in all of these models, the proppants that we have used were actually the proppants that were used in the actual operations. So for example, like the ranges would be, there would be some 4070, some 100 mesh, and so on. So usually the usual range of proppant sizes that we encounter in the basins.
And then the next question, apologies for in this individual arriving late, but he wanted to know if you said that the completions were parallel to the intrinsic fracture network.
Um, I'm not sure I, if I fully understand what the question says, but yeah, I mean, in in the in most of these data sets, when we look at the fiber and the frac hits, we see that the fractures are propagating along the SH max. We've not considered like a complex fracture network, but planar fracture propagation. I think if that was the question.
I think that's a good answer. Yeah. So now a little more specific.
Yeah,
Robert's interested in slide 20 and
yeah.
whether proppant embedment can be one possible cause for reduction with time.
Yes, that's a good question, Robert. And the answer is yes. Um, so we have in some of these data sets, we do have a proppant embedment kind of applied. And so kind of you can think of that acting in parallel. Maybe this could be a good one to show. So for example, we have a higher amount of productive area after 6 months and a lower in terms of 2 years. You can probably reach some of this by having a stress dependent embedment as well in the model. So for example, when we increase the effective normal stress on the fracture, more proppant gets embedded. And certainly some of these data sets have some embedment factors. And in addition, uh, some of the time dependent kind of proppant conductivity loss is in addition to the embedment. So yeah, we have both the factors at play that we need to calibrate some of these models. So good question.
And Zeno's question is related to slide 17. And I'm not sure you can see the question, so I'll read it.
Yeah,
Gauge 6 and 7, there appears to be a large pressure difference.
yeah.
What is the distance from the producing lateral? And can that be considered preferred lateral spacing? And is this reproducible elsewhere?
Yeah. So again, a very good question. So for example, this, and as I mentioned over here, if you see on in the paper as well, we mentioned this cliff. This is indicating that probably this is the edge of the more productive area. So kind of the hypothesis is that till this distance, which is gauge 6, we have a significant amount of proppant such that the proppant concentration is high enough to get more depletion. And then when we go from this to gauge 7, is that's kind of the edge, maybe. Yeah. So for example, we have high proppant conductivity decreases, and then we go to the edge where we go from a proppant that can contribute significantly and uh, to a lower proppant concentration that doesn't contribute significantly. So that's probably the distance between gauge 6 and gauge 7. uh, I think yes, the answer to your question is this could be kind of a preferred lateral spacing, as if you're looking to maximize production, for example, then you would have you would know that your maximum drainage is happening at these distances. Of course, adding the caveat that well spacing kind of depends on a lot of different functions, such as the objective if you're trying to maximize production or NPV, etc. with those caveats, yeah, with if you're trying to drain kind of efficiently every block of rock, then probably yeah, this could be a good estimate of distance. Uh, if it's reproducible elsewhere, I think the exact distance would vary, as we've seen with, for example, the operational design, the stress profile, etc. So the number of the distance will not be reproducible elsewhere, but the approach of finding out how far we are draining and then using that insight to get the well spacing is certainly reproducible.
Now, Omar has a question that'll be close to your heart
Yeah.
and interested in, can you elaborate on which logs you rely on to estimate stress as well as how you relate them? Possibly you just want
Yeah.
to give a reference because that maybe is a 30-minute answer.
Yeah. So Omar, kind of, for example, the cases I'm showing here, the stress profiles were computations were done by the operators. And yeah, I think a lot of people in the industry use the extended Eaton's model. There's the Blanton and Olson paper, Thyssen and Plumb. And we've also kind of, for a lot of cases, are now using the viscoelastic stress relaxation model, which I worked in my PhD, and Mark Zobak and a lot of his students have worked on that. For example, if you look at the Delaware Basin in HFTS2, we were able to explain the height growth by looking at the viscoelastic stress relaxation, where we are looking at some of the elastic properties and viscous properties of rock and pore pressure. So a different suite of rocks, but yeah, I think kind of, yeah, you can look at Singh and Zobak 2022 is a good reference for the viscoelastic stress relaxation. And for the extended Eaton model to look at what parameters we use, Blanton and Olson is probably the best reference, I think.
Very good. Now, El Hakbani, his question is once again related to slide 23 and the role of the minimum horizontal stress on effective stress on proppant. What is the role of the maximum horizontal stress and stress anisotropy on conductivity?
That's a good question. So I think uh, for the for a planar fracture, the maximum horizontal stress is probably less important. It is a factor when we kind of are resolving the stresses that act on the fracture plane, and when we are looking at, for example, poroelastic stress changes, etc., and calculating the fracture apertures, the stress anisotropy does play a part. But for example, because the fractures are opening perpendicular to the minimum horizontal stress, so that's probably more important component in this case compared to the maximum horizontal stress. Now, of course, now when we talk about fault slip and all the other cases, maximum horizontal stress becomes equally important. So yeah, for the planar fractures, probably more important to know SH min, but again, for an integrated analysis, SH max becomes very important as well.
So we're running out of time, but I'll give Sam French the last question. And Sam's
Yeah.
question is, did you set a fracture conductivity limit or proppant concentration limit for calculation of effective fracture half length? And he's wondering if the cliff indicating the edge of significant proppant concentration would indicate these values to determine effective fracture half length.
Yeah. So again, great question, Sam. Maybe I will go to this figure. So we have kind of, if we look at this figure, the proppant conductivity decreases as we go away from the wellbore. And as we decrease the proppant conductivity, the contribution of the fracture element is for example, calculated numerically. So for example, if I go over here, the proppant conductivity is so low that when we have drainage from the matrix into the fracture, there's no way of the fluid to make its way to the wellbore. So for example, we look at the connected conductivity, and when that's high enough, you will have a significant contribution to the fracture. So the conductivity is calculated as a function of the proppant concentration. And when the proppant concentration is low, the calculated conductivity becomes low, and so it kind of becomes unproductive in that sense. So there's kind of no hard cutoff applied to the production, but it's just calculated. The conductivity is calculated as a function of the proppant concentration, and the production contribution of each fracture element is kind of would be calculated on how it's connected with the wellbore.
I'm afraid we've run out of time. There's still a number of questions left, but I'm sure that if you reach out to Ankush, he'd be happy
Yeah,
to address those questions. And if you're too shy to do that, reach out to me and I'll pass the question
for
on.
sure.
Thank you, Ankush. Great talk. This is recorded and will be available on the ARMA website. And thanks everyone, and thanks Ankush.
Thank you, John, and thank you everyone for listening in. And yeah, really enjoyed the many questions that you all had. So thank you.
Hey, that was awesome.
Thanks, John.
Let me just turn off the recording.